can. And we're ready to go. All right, everybody. So right now we are starting to do a little bit of review on our homework. And we're talking about problem 617. We had a question about the angles. Now, first of all, if you started at point D, I would be concerned because you have 3 unknowns. Okay? So that would be a very difficult joint to start out. I would probably do my statics first. Always do your statics first, no matter what. Find out the reactions at A and B. And then after that, I would work my way up. You know, but always look for a joint where there's only 2 reactions. But the specific question is, what does the geometry look like and what do my forces look like here at point D? And that's a very good question. All right. Well, if we draw this out, now I'm not sure you can see what I'm drawing. No, you cannot. Let me widen this out. Okay, there we go. So this is what D looks like. And what you really want is this angle, all right? Because we're still resolving everything back into x and y components. So that's kind of the big deal. So let's call this dB and this dA. Now, one thing I want to show you is, because we have a force of 150 pounds here, that is symmetrical, but this 75 kilonewton force kind of throws everything off. So we're not going to be able to really use symmetry in this, are we? Okay. In the second problem in 621, the forces are applied symmetrically and the distances are symmetrical, so we can use symmetry here. But here we're kind of out of luck. We're going to have to look at every single structural member. Okay. So what is that angle? Well, what we are told is that this distance is 2 meters, and then the distance down to the bottom is also 2 meters, and this distance is 5 meters. Okay, so if we're looking at this angle, it's really based on this triangle where we have 4 and 5. So the vertical distance to the is 4 and 5, or if you knew this distance, this is 2. If you knew how far it was this way, you could use that angle. But here's where I have all of my data. So if I call that angle, let's just say angle D, we have the opposite and the adjacent side, opposite, adjacent, and that is tangent. So the angle of D is the inverse tangent of 5/4. Okay? Now, in order to use that, when we look at D sub B, for example, we're going to have D sub B in the x direction and D sub B in the y direction. In the x direction, since this angle is here, this is opposite, isn't it? So D sub B in the x direction is the entire force D sub B. Opposite over hypotenuse is the sine of angle D. And so this, because it's adjacent, would be dB cosine of the angle of D. Okay. And this all harkens back to trig, which may have been a few years since you guys were doing the trig. But yeah, it can be confusing if you start looking at, well, what about this distance or that distance? But we're always taking everything back to x and y. You know, those are the coordinates that we'll use almost exclusively in this class, is Cartesians. Yeah?
I don't know about the other guys in the class, but I think my biggest issue is I'll get to working and I just lose my train of thought.
Oh,
so,
yeah.
Like, is there some sort of
way to keep your thoughts organized?
Well, just like maybe.
I didn't mean that as a joke. I was serious.
It's like a concern.
You can meditate a little. No, I'm just kidding. So.
No, is there something like just a list of
like steps,
procedural steps like that we can?
Yeah. Yes, this is what I would do, and so as sort of like a method or a cookbook, the first thing that you should always do is your statics on the entire structure. So the external statics on the structure. Okay? So in other words, when I look at this, I'm going to bring up, because they draw nicer than I do. The first thing I would do is do a free body diagram of the entire structure, right? So I don't even care at that point about these, what these look like. I have a 150 kilonewton force pushing down, a 75 kilonewton force pushing up, a rolling support here. So all this is going to bear is a Y. So I have A direction, A in the Y direction. B is fixed, so I'll have a reaction at B in the X and a reaction at B in the Y. So that's the first thing I would do. So here I would say summation forces X equals 0, summation forces Y equals 0, and that's on the entire truss. I don't even know what I'm spelling today. I apologize. Okay, so in the X direction, what do I have? Negative 75 kilonewtons. I don't have anything that's going to be born here because this is a rolling support. So that means that the only, I'm going to have a reaction at B in the X direction, and I've drawn it as positive, equals 0. So what does that tell me? It tells me that the reaction at B in the X direction is 75 kilonewtons. Okay, so I'm just looking at the externals here. Now, what about on A and B? Well, I have I'm going to draw it positive. Doesn't mean it really is, but this would be the reaction at A in the Y direction, the reaction at B in the Y direction. So the way I have it drawn is the reaction at A in the Y direction plus the reaction at B in the Y direction, I should say minus 150 kilonewtons equals 0, and then I get equals 150 kilonewtons. All right, now, let's do this. We don't know because of this force if symmetry is going to take hold and if 150 is going to be equally divided. So we need a third equation, and the third equation I would use is the summation of moments about some point on the entire truss has to equal 0. It doesn't really matter, but I would choose point B, maybe, just because there's two forces there. And if I take the moments about point B, if I use B as my pivot point, then the reaction at B in the Y direction and the reaction at B in the X direction have no moment arm, so the moments from those forces about B would be 0. Okay? So, having said that, let's take a look. I have a reaction at A in the Y direction, which is vertical. That means I use the horizontal moment arm of 10 meters. And then I decide if I put a pin here and I pulled on A, that would be clockwise, which is negative. And then the 75 kilonewton about B, it's a horizontal force. So the distance is the vertical distance of 2 meters. And if I were to put that pin there and I only had that 75 kilonewton force, that would be counterclockwise, positive. And then the last but not least, I have the 150 kilonewton force. I don't even know what you can see here. I need to pay attention. Here we go. Since that's a vertical force, we have the horizontal distance of 4 meters. I'm not going to go through this laboriously, but I'm just kind of going. So then that would make a counterclockwise. So that's positive equals 0. I can use this to solve for RAY. And plug that in here and solve for RBY. Okay? So this is the first thing I solve for, this is the second thing I solve for, this is the third thing I solve for. Okay. The next step is, now we have those knowns. My reactions at A and B are known. So the next thing I need to do is to choose a joint with 2 or fewer unknowns. Because in the method of joints, we can't use the moment equation. All we have are summation forces X and summation forces Y. So if we have 2 equations, we just can't have more than 2 unknowns and solve for them explicitly. Okay? So if we choose point D, we have 1, 2, 3 unknowns. And so that's why that one doesn't work as well. If we chose C, we also have 3 unknowns. But if we choose A or B, we only have 2 unknowns. So when you do that, if, for example, we look at A, we have the reaction A in the Y direction, which we just solved for here. And then we have some component of AD and we have some component of AC. Okay, this is purely y. Summation force is y equals 0. So we have RAY. We have to choose directions. At least one of these is going this way, and one of them has to go this way, because these are the only two with x's. So if one's pointing to the left, the other one has to point to the right. But since this one is pointing up, one of them has to be pointing down. Okay, so here I would have RAY minus AD in the y direction plus AC in the y direction equals 0. And then summation forces x equals 0. There's nothing here, so we get AD, it's negative in the x direction, plus, sorry for being left-handed, AC in the x direction is equal to 0. And then you can do your trig, get your angles, and do cosines and sines. So the third thing is trig to finish. Okay. Excuse me. All right. So then you start writing a table. Okay? Your answers are going to look like this. AC equals this many kilonewtons in either tension or compression. So we have AC, AD, DC, DB, and CB. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, and that's what you want in each of them. So the next part is, after you choose joint A, you now know, so this would be step 4, since you know AD and AC, you can move to another joint. And because this time, since you have more knowns, D, for example, AD is known from here. So that means that here you would only have 2 unknowns. So you could move to joint D. So you just remember that the force, the tension or compression in AD is going to have the same magnitude at both joints, right? If it didn't, it's either going to be in tension or in compression, but the magnitude is going to be the same. If it weren't the same, that structural member would just fly out of the structure, because force equals mass times acceleration. So there's no way that that can have a net force other than 0 if it's standing still. Okay? So I guess this process would just be called maybe chasing chasing the internal reactions. Okay? And so you find those and you just work your way down the list, and there you go. So the best way to stay organized with this, I think, is I always start with that table. You know, it's like, these are the things I need. So when one of them pops out, you just sort of go, there it is, you know. And then the other way to stay organized is to just use an awful lot of paper. Because it's better, if you think about this, this is really like 5 little problems. It's like you do the same, you know, you do the statics, but then you have to chase those reactions through the truss. And it's really like 5 different, you know, depends on how you do it. But you may do 3 or you may do 5 joints. But after you have your table pulled in, then you're done. So is that any help? Yeah. Okay. And it's a good question. Even though your classmates thought it was a funny question, I thought it was a good question. So. All right. What other questions do you have? Okay. What I want to do today is a little bit different. I want to just go into what we're going to do with these forces once we find them, which is find sigma. But I've got the vodcast and the YouTube posted for you now. We've gone over this again. So you still need to finish this homework, but we're going to kind of pretend like we did this already and move on to finding sigma, or normal stress, and see what that looks like. Okay? So we're going to go into our actual textbook. Does anybody need to borrow a textbook today? Yes? 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 Oh, you have a textbook that's right under here.
Oh, I don't know.
Yeah, we'll just use that.
Okay.
That'll be fine. So, here. You? Does anyone else? If you don't have a textbook, yeah, maybe. There you go. Why don't you guys share and let him, there you go. There we are. So, all right. And so what I'll do is, I'm going to look at chapter 1 problems, and I'm going to try to find one that looks exactly like a problem that you have or similar. Okay. All right. Let me see. May I look? Oh, perfect. So you've got this one. Okay, my dimensions are a little bit different. Okay, but I'm going to work problem one. If you're in the old text, we're going to work problem 1.1 and possibly 1.2. They sort of go together. In the new text, we're going to work 1.3 and 1.4. Okay? And if you're in the old text, your dimensions, the drawing is exactly the same, the process is the same, but the dimensions are a little bit different. So you'll have to kind of play along with that. All right? I'll try to be really explicit so that we can finish this up. All right, hearkening back to our first day of lecture, we learned that normal stress equals P over A, some load and some cross-sectional area, and that this load is an internal response. Now, we also designate normal stress with the Greek letter sigma. And this, there are actually two versions of sigma. You may be familiar with this one, which is summation, and this one. This is capital sigma, and this is minuscules. This, they call it majuscule. It's not really capital, but it's majuscule and minuscule. But this is the form of sigma that we use to designate normal stress. Okay, so on problems 1.3 and 1.4 in the new text, and 1.1 and 1.2 in the old text, the problem reads, two solid cylindrical rods, AB and BC, are welded together at B and loaded as shown. Knowing that P is equal to 10 kilopounds, find the average normal stress at the midsection of rod AB and at the midsection of rod BC. All right, so as always, we start out by drawing. All right. Now, the good news about engineering drawings is you really don't have to be a gifted artist. You just have to be able to simplify a problem to its minimum required components, which some of you may be very artistic, but for me, this is a good idea. So whenever I draw something like this, I always think of it as being like the engineering equivalent of a stick figure. So, you know, like you have a stick figure guy, and you just put on like the most important things that indicate that this is a human being. So this is Ernie, our spokesmodel. So Ernie helps us sometimes draw things like that. So if you want to simplify things, just think like Ernie. You know, you don't want to have like the beautiful stuff. You just want to have something very, very simple. All right, so Ernie will draw this picture. We have a P down here, which I'm told is 10 kilopounds. And here at B, we have a different force, which is 12 kilopounds. Okay, we're attached to the wall, or to the ceiling rather, and here at B, we have a welded joint. What that tells us is this is not going to pull apart. That the load, P, the 12-pound load and the 10-pound load, or 12 kilopound load and the 10 kilopound load are going to be distributed on this structural member in a way which we're going to determine in just a couple seconds. And it's not going to pull out of the ceiling, and the weld is not going to break. Okay, so we're kind of making that assumption, but it's a valid assumption at this particular point. All right, so let's find out what we know. We know that we have, let's talk about the ceiling here. Where it is attached to the ceiling, if we're pulling down with 12 kilopounds and 10 kilopounds, how much is the reaction at the ceiling going to be, do you suppose? Assuming it's not going to pull out. Ah, exactly. That is exactly correct. So once again, we start with the statics. And we have a reaction at the ceiling, which is point A, right? So we say summation forces Y equals 0. I'm just doing what you already did in your head, so this is very good. So at B we have negative 12 kips, and down here at the bottom we have negative 10 kips, and then we have a positive reaction at A, and the three of those things have to sum to 0, otherwise it was going to pull out at the ceiling. So R sub A then is equal to 22 kips. That's the first important thing we need to find out. Now here's another question for you. If you look at these two sections, do you think that the internal load in this section is the same as the internal load in this section? Because if you think about it here in AB, we have 22 kips pulling up and 22 kips pulling down. But here in BC, if we were to cut away in the middle of this, we only have 10 kips pulling down, don't we? This 12 kips is just moving it, but it's not actually putting the lower part BC into stress, is it? Okay, so the first thing we need to realize is that the internal stress here in AB, or the internal load in AB, is, in this case, and often is different than the internal load in BC. So we have to do statics on both parts after we just found out our reaction at A. And the way we do this is called a cutaway. Remember, in mechanics and materials, or I don't know if it's called a cutaway, that's what I always call it, so there you go. In mechanics and materials, we're always looking at the internal response, okay? So let's look at part AB of that rod. If we just draw part AB from the ceiling to the midpoint, which is not meaning exactly in the middle, it just means not at the edge, okay? We recognize that R sub A is pulling up with a force of 22 kips. And so we're going to have some reaction here in AB that's pulling down. So the summation of forces in the Y is equal to 22 minus the reaction in AB, which is equal to 0, or 22 kips is equal to the reaction in AB. Now, tell me something else. Is AB in tension or in compression? It is. It is absolutely in tension because it's being pulled away from the ceiling. All right, let's do the same thing for BC. In BC, let's cut away again. And this is the midpoint of BC. Once again, not exactly in the middle. It doesn't have to be, but just sort of in the middle. Here, all we have against it is 10 kilopounds pulling down. And here we'd have the reaction in BC. So when we do the summation of forces in the Y direction equals 0, we get the reaction in BC, which is positive, minus 10 kips equals 0, or the reaction at BC is 10 kips. And once again, it's in tension. Now, when you cut away, you're only concerned with everything above just becomes a reaction. So you're only concerned with the external loads on one side of the reaction. What would have happened if we would have cut it the other way? Well, it would have come out to be exactly the same, which is the good thing about math and engineering. If you do it right, it comes out to be the same. If we had instead cut it this way, so that we had our reaction down here, we would have a 12 kilopound load pushing it down and a 22 kilopound load pushing up, pulling it up. So when we did the summation forces Y equals 0, we would get minus 12 plus 22 minus the, whatever I'm calling it, the reaction at BC is equal to 0. So we would get the reaction at BC is equal to 10 kilopounds. So it's exactly the same. So I wanted to show you that because it's more complicated to do it that way, but it does not matter which way you cut away. The only thing that you need to know is that after you make that mental slice, you only look at one side, and everything else becomes the reaction. And it always adds to 0, or else it's going to start to move. So that's sort of the analysis process. Okie dokie. Continuing then. So we know, let me get this down, that the reaction at A is equal to 22 kips. And no, I don't want to put that. I want to use this kind of labeling. The reaction in AB is equal to 22 kips, and its tension. And the reaction in BC is equal to 10 kips, also in tension. Okay, so what are my sigmas? Sigma in AB equals 22 kips over the area. Sigma in BC equals 10 kips over the area. So now we need to go back to our picture. What is the area? Oh, I never did this. I always did this. What is it? Well, let me get some dimensions here because I didn't really put out all of the dimensions on this since we have different books. Okay, we're told that this length is 30 inches. We're told that this length is 25 inches. We are told that this diameter is 1.25 inches. And we're told that this diameter is 0.75 inches. Okay? So these are cylindrical rods. What is the cross-sectional area of a cylinder? What shape is it? Cylinder? Yes, circle. Very, very good. I knew you knew. Okay, so the area of a circle is either pi r squared or pi d squared over 4. And we'll just use pi r squared because it's easy enough. So here we have 22 kips over pi r of AB squared. And here we have 10 kips over pi r squared of BC. So let's find out the area of AB and the area of BC. The area of AB then is pi times, if AB has a diameter of 1.25 inches, it has a radius of half of that, or 0.625 inches. We square that. And BC, pi times half of 0.75, which is 0.375 inches squared. Anyone have their calculator at the ready to tell me what those areas are? Um, 0.625. Okay, when I do this one, I get 1.227 square inches. And if you guys get a different number, please tell me, because I'm doing with this little fake calculator on the computer, so it's not very advanced. And for the other one, I get 0.4418. Does that look correct to you? Mm-hmm. Excellent. Thank you, Jacques. All right. So now let's finish off the job. That means that sigma in AB is going to equal 22 kips divided by that cross-sectional area of 1.227 inches squared. Now we'll do the math, we'll do the numbers, and then we'll decide what the units are going to be. 22 divided by 1.227 is 17.93. And let's just do this since we're kind of on a roll. That will be 10 divided by that cross-sectional area of 0.4418, which is 22.63. We'll talk about what those mean in just a minute. And what are my units? Well, a kip is 1,000 pounds per inch squared. A pound per inch squared, a pound of force per inch squared, is a unit called a pound per square inch, which is abbreviated PSI. Or a kip, which is 1,000 pound per inch squared, is a unit called a KSI, kilopound per square inch. So this number is in KSI, and this number is also in KSI. Or you could write this equally correctly as 17,930 psi. Or you could write it as 17.9 times 10 to the third psi. Any of those things are fine. But this gets into sort of our strange U.S. customary system of units. It's not really even a system. It's just a whole bunch of stuff that's thrown in together. So, and then we kind of go, well, but 1,000 is kilo, so let's call 1,000 pounds a kilopound, which doesn't make very much sense, but there we are anyway. Okay? All right, so these are our answers. Let me ask you a question. If you notice, the load in AB is larger than the load in BC. However, the stress is less than it is in BC. And why is that?
The member's further away.
Well, the member is smaller.
Yeah, gotcha.
Yeah. So what that means, and that's a really, and there are some times where we're going to talk about distance. That's why it kind of got my attention. But right now, what we're talking about is smaller. So what that means is you can put more load on something that's bigger, right? I mean, that makes sense. If it's stouter, you can put a bigger load on it. That's why we don't build houses in real life out of toothpicks, right? And then later on we'll get to the distancing, which is why you don't build houses out of silly putty. You know, you build nice big wood structures or steel structures if you live in somewhere with termite problems. All right. So that's the material that we're going to cover. That's the material that we covered today. That's going to go along with the stuff that you did last time to sort of get us to where we are, where we need to be. At this point, you guys have any questions? Okay, so the homework for tonight, in addition to the material that we just covered and that I put up on YouTube for you, we need to do 2 more problems. One of them is going to be very similar to the one we just did. And these are both in the new textbook. So if you have the old textbook, you need to get a copy of the homework problems from the new textbook. So the 7th edition of the textbook. The problems that I would like you to do are 1.1, which is similar to what we just did. And then there is a frame. I wonder if I want to do that one or if I want to do a different one. Let's do problem 111, which is a Pratt truss. Okay, it's a type of a bridge truss. So they're asking you for the average normal stress in member BE, which means you're going to have to use the method of joints to find the tension or compression in BE, and then divide it by the cross-sectional area. So the easy part is once you find the load, dividing by the cross-sectional area really doesn't freak people out, except for the unit part, but getting to that point is the more difficult thing, okay? So those are the 2 problems. And I also want to apologize to you for not getting the video boosted until this morning. The person who does it sent it to me a while, like maybe yesterday or maybe even Monday afternoon, and it just kind of got buried in my Outlook box. So I will try more diligently to get the videos put up for you right away, okay? Sometimes he's not able to get them to me immediately, but as soon as he gets it to me, I'll put it up on YouTube. This time it was not him not getting it to me immediately. It was me just not seeing it. So anyway, so I'll get those to you as soon as possible, all right? All righty. So I'm going to turn off our streaming.